Okay, so I'm doing soils and climates. And let's see, I'm not sure why, but Mike Vasey, you still got this. Oh, no. Do you see me, Mike? His microphone's off. Okay. Um, I'm going to just do this. Okay. I think we can
I
go.
do see you.
All right, good. Because I see you, and that scared me for a while, but now I'm getting used to it. Okay, so I'm going to talk about climate and soil of San Bruno Mountain. Now, here's San Bruno Mountain, and we've talked about it all day long and how it's got so many unique things. But I always wondered what makes it so special? Why are there unusual plants here and say they're not over elsewhere? Well, Jepson in 1925 had a concept, and he found zones of high endemism in California. And his zone number 10 was the Pacific zone, and he called it the Franciscan zone. Now, he called it the Franciscan zone after the Franciscan formation. And just as rocks have a type, plants have a type location, so do rocks. And the Franciscan zone's type location is San Francisco. So he thought there was a zone of high endemism. However, Roof, who was more intimately associated with the plants of the Bay Area, he said, no, actually, the zone of high endemism includes most, but not all, of the San Francisco Peninsula, San Bruno Mountain, and a very small part of the Marin Headlands. And he called this the Franciscan landscape. Now, the difference between a landscape and a zone is simply landscapes are smaller in area. So Roof first said it's this smaller area, and then subsequently it's been called a Franciscan landscape. So the Franciscan landscape has unique plants, but our question is why? Why are these unique plants and other areas which are really close by, they're also mountainous, they're also coastal fog, why are they different? Well, I think there is an answer, and the answer lies in geology. Now, this is a fairly obscure paper, and you can see it was typed up. It was not even typeset, and it was published by the U.S. Geological Survey, and it's the technostratigraphic terrains of San Francisco Bay region. Now, this is a diagram based on that, and you can see right here the San Bruno Mountain terrain. Now, the San Francisco Peninsula is also composed of the Marin Headlands terrain and the Alcatraz terrain. But what's a terrain? A terrain is a fragment of coastal material that's been scraped off one tectonic plate and accreted onto another tectonic plate, and it's surrounded by faults, and the rock has a unique geologic history from the surrounding areas. Now, what does that mean? Can I express that in an example? Well, geologists like to use the Oreo example. If you take an Oreo and you shear it apart, the creamy filling forms these lines. It's very much the same thing as if you had mud on your boot and you went over to a rock and you scraped it off several times. Each time you scrape it, you'll have a separate piece of mud on the rock. Well, that in a tectonic plate formation would be called a terrain. Now, the Farallon plate, which is oceanic crust, and oceanic crust is heavy, so it's going subducting below the western edge of the North American plate. That's a continental plate, and continental plates are light. So the Farallon plate goes below the North American plate, and it scrapes off bits of rock. At California is basically 33 different terrains, and San Bruno Mountain is its own terrain. It's gray wacky with just a little bit of serpentine. And as the Farallon plate dove underneath the North American plate, the San Bruno Mountain terrain was scraped off onto it. We know from other work that it's formed from sandstone that came from the Sierras and granite, but that's a different story. So this is a terrain. So the Franciscan landscape has unique plants because of unique geology, and it's the San Bruno Mountain terrain. Now, therefore, we've got similar plants to San Francisco because they also have some of our geology. And the idea here is if you want to see the plants of San Francisco as they were in 1816 at the time of the Kotzebue expedition that came in on the Rurik, and on board had the names that you recognize from so many plants: chamiso, chorus, eschscholtzia, and romanzoth. Come to San Bruno Mountain. We've got the plants that San Francisco paved over and no longer has. So San Bruno Mountain State and County Park. Why is it unique? It's got unique geology. But that's not the only thing that makes it unique. It's our water. California, as you all know, has a Mediterranean climate, which is defined as cool, wet winters and warm to hot, dry summers. And as Mike Vasey has in one of his publications, we have the driest summer of any Mediterranean climate. So we've got very warm, hot, dry summers, and that is a significant stress on the water budget of plants. But what we've got is fog. Fog is sitting out over the ocean, and all you have to do is be on San Bruno Mountain around 1 o'clock, and the fog comes right in, and you can see it. Now, the fog of the atmosphere has a significant amount of moisture. In fact, the atmosphere is the second largest body of water on the planet, and the onshore breezes bring it into San Bruno Mountain. And on the driest year in a century, in the middle of August, I sat underneath that tree right there, and it was so wet from the fog that my pants got wet. So fog brings in a significant amount of moisture. And the moisture comes down so much, you think that it's rain, because this pool of water is not formed during a rainstorm. This fog, or that rain, is coming from fog in the fog forest. So tree drip is the fog's effect on water budgets. And we've been taught this for a long time, tree drip. But the question is, where are the trees? I mean, San Bruno Mountain doesn't have very many native trees. Most of our tall forests are exotic trees, the tall eucalyptus, the tall Australian weeds, as well as some Monterey cypress. So tree drip is there, but where are the trees? Now, it's been studied. The quantity of tree drip is proportional to the cross-sectional area of the tree, and it decreases exponentially away from the windward side of the trees. So the tall trees are going to create tree drip, but we don't have a lot of native tall trees. Now, James Roof observed that the fog drip that the exotic trees create adds an abnormal amount of water to the understory, and the result is a microenvironment that is not representative of the Franciscan landscape. So here is a grove of tall Australian weeds, and if you look down at the bottom, all there are weeds. There's English ivy, there's Himalayan blackberry. About the only native plant there is poison oak. So tree drip from fog is not what gives rise to the unique plants on San Bruno Mountain. It has to be something more. Well, what is it? If it's not tree drip, what does fog do? Well, fog causes decreased evapotranspiration, increased foliar uptake, increased humidity, decreased temperature, and decreased solar radiation. Now let's look at each of these concepts in turn. Decreased evapotranspiration. Photosynthesis requires a constant amount of CO2, so therefore leaf stomata have to be open for C3 photosynthesis. There are 3 different kinds of photosynthesis. Here we're just talking about C3. So here's the stoma, and it's open, so CO2 can come in and the O2 can go out. But what's also happening at the same time is water is leaving. And the water leaves the stomata at a huge rate. That is, the humidity of a leaf interior is 100%. And 98% of the water brought into the plant by the roots is lost to evapotranspiration. And 400 water molecules are lost for each water molecule of CO2 that's gained. So evapotranspiration is a huge effect on the water budget of a plant. So although fog drip is the most obvious effect of fog on plant water budgets, outside of tall forests, the most important effect of fog actually is decreased evapotranspiration, and this has been written about by scientists. Foliar uptake. Mike and I were just talking about this a little bit. Roots are not the sole path for water into a plant. They can also come in through leaves and stems. And you can prove this by taking a sprayer and spraying various plants. If you spray sword fern, it has a tremendous water uptake through the leaf. This may be why normally I'll see sword fern in redwood forests, places where they're shaded, but you'll notice on San Bruno Mountain, they'll be out in the straight sunlight. That's probably because they're able to survive with foliar uptake from fog. Now, not all plants have good foliar uptake. The California bay laurel, with its waxy leaves, has very little foliar uptake. Okay. Fog's other effect is increased humidity and decreased temperature. Now, this is independent of evapotranspiration, but by having high humidity, you decrease water loss from the plants. And the other is decreased solar radiation, so you have less moisture loss from the soil. So the combined effects of fog are actually rather complex. Fog drip is generally not important on most of San Bruno Mountain because the size of the plants are very low, and fog drip is proportional to the height of the plant. However, there are other important effects. Decreased evapotranspiration is the single most important effect on San Bruno Mountain. And we've noticed that with the exception of one group of Arctostaphylos imbricata, all of our manzanitas are about 100 meters below the crest on the lee side of the mountain, where fog would recirculate. And because we've noticed in experiments that the manzanitas have great foliar uptake, that may be why our manzanitas are located at that place. The other fog effect is increased foliar uptake, increased humidity, and decreased temperature, independent of evapotranspiration, and decreased solar radiation to the soil. So we have an unusual bunch of plants on San Bruno Mountain, and it's probably because of geology and climate. Thank you.